If you remember, we have finished, I think, the second section of that chapter, and we were about to start for the third section.
For what? The fourth chapter?
Fifth chapter, we have finished the second section. There were three sections. We had finished the observation and experiments from sampling survey.
For observational study, the stratified and those stuff.
Correct. Yes. This is chapter 2.
Yeah, okay.
Oh, okay. Yes. Yeah, we were here. Okay. Okay. Using studies wisely. So we had finished the last topic. That was placebo effect and all that. The block what you see, match pair design, block design, randomized design. Yes, we had done that thing. We were about to start. We have done this example also, and now we'll start 4.3, studying studies wisely. Topic 4.3. So I'll just on our Miro board. I have forwarded the second test to your mom, so you can give that based on the second chapter. You can give that, I'll evaluate that, and I have forwarded the evaluation of the first test. There's one what you'll say missing thing in the test, that was elaborating the answers. Means you have to write about the answers in a very brief and big way, so that it is much more explainable why it is right skewed, why it is left skewed. Yes, so that is that looks very good when you elaborate things. That gives a positive what you'll say mindset to the teacher.
Yeah, okay.
Okay. Okay. Now we'll start with using studies wisely. So using 4.3 it is using studies wisely. As okay. Okay. So what is in there? So researchers who conduct statistical studies often want to draw conclusions that they go beyond the data they produce. Here are two examples. The US Census Bureau carries out a monthly current population survey of about 60,000 households. Their goal is to use data for these randomly selected households to estimate the percent of unemployed individuals in the population. Scientists performed an experiment that randomly assigned 21 volunteer subjects to one of two treatments, sleep deprivation for one night or unrestricted sleep. The scientists hope to show that sleep deprivation causes a decrease in performance 2 days later. What conclusions can be drawn from a particular study? The answer depends on how the data were collected. So we have seen all the things. The output also depend upon the way the data was collected, and the output also depends upon the design that we are doing. So there we have run in the previous section different design, randomized block design, match pair design. So if you remember, I'll just revise what we were doing in randomized design. We were first of all, this was a group, for example 20 students. We were dividing them into applying random selecting, and then dividing them into two equal groups, 10 students and 10 students, correct? Then giving them different treatments. If it is having caffeine, it will have not having caffeine. Then we were observing the comparing the results. This was comparing result. This was general random design. And what was block design? we used to make different blocks depending on the similarities. For example, there are 20 students. Okay, so suppose we have made two blocks in that, one having diabetes and then other having non-diabetes, correct? Okay, then
Yeah.
in that we generally random assignment. Okay, then random assignment here. For suppose here we'll do random assignment as having caffeine, not having caffeine. Here also having caffeine, not having caffeine. Then what you will do, compare the result. Here we also compare and here also compare. That's the thing what we have learned. And in matched pair, what we have done, if there are 20 students, for example, we'll make a block of two students. Yes or no? Matched pair. We
Mhm.
have to make a pair of two students that matched in a specific, what you will say, specific property. And then we'll observe the changes. And in that also we have learned that for one student, we can do two times the experiment. For one student, we'll have having caffeine, not having caffeine. This was the first day. Then in the second day, what we can do, flip our, what you will say, treatment. Flip our treatment. Here it will be having not having caffeine, here having. So this was all that we have done till here in the previous section. Okay. So now he is telling that in this section, now inference of sampling. What does inference means? Inference. See, what does inference means? Inference. And now he's trying to explain how, what you will say, the output depends upon sampling. Inference of sampling. Inference means conclusions. Inference meaning conclusion. What do you conclude or what do you predict? Also, you can say predict in the manner. Infer, predict. Okay, so that's the thing. Means what effects are there on of sampling on our output. So we'll see these things in the this section. Okay, when the members of a sample are selected at random from a population, we can use the samples to infer things about the population. Correct. So a sample when a sample is taken, for example, this is a population and I take a small part, this part as a sample of the population. So what we can do, after performing experiments on it, we can make conclusion or make conclusions or infer, means to predict something, infer about the population. That's the thing. When which population? The population from which we have chose the sample, not some other population. So that is, we can make inferences about the population from which the sample was randomly selected. Inference from convenient samples or voluntary response samples would be misleading because these methods of choosing our sample are biased. Choosing a sample are biased. In these cases, we are almost certain that the sample does not fairly represent the population. So while sampling, so while sampling, it is better not to use. We have seen these many times. Convenience, convenience, and voluntary response sampling and voluntary response sampling. That is the thing. Okay. Voluntary response sampling. So in these cases, we are almost certain that the sample not fair. Okay. Even when making an inference from a random sample, it would be surprising if the estimate from the sample was exactly equal to the truth about the population. For example, in a random sample of 1399 US teens age 13 to 18, 26% reported more than 8 hours of entertainment media use per day. Means the students were 26% of students were using 8 hours. more than 8 hours of their cell phones or any entertainment social media app. So because of sampling variability, it would be surprising if exactly 26% of all US teens aged 13 to 18 reported more than 8 hours of entertainment media use per day. Why? Because different samples of US teens aged 13 to 18 will include different sets of people and produce different estimates. So now we are saying that if we selecting different samples from the population gives different results. These differences in the results, so we'll come to the topic. These differences in the results, differences,
Mm.
or you can say variability in the results are due to are due to our
Mm-hmm.
random sampling as in each sample as in each sample it can happen each sample there will be different sets of people, there will be different sets of people. That's the thing. So there's a
Mm-hmm.
variability between different samples of the same population. So what it is called? So sampling variability refers to the fact that different random samples of the same size for the same population produce different estimates. So there's come the main topic, that's sampling variability. Sampling variability. So what is sampling variability? Same same size same size, different samples, same size, different samples of the same population, of the same population gives different estimation, gives different estimations. This is known
Mm-hmm.
as sampling variability. That is the sampling. This is known as sampling variability. Is it clear? What is sampling
Yeah.
variability? Come on, read this question and give me the answer. Come on. We'll go through it. It is an activity exploring sampling variably. When making an inference about a population from a random sample, we shouldn't expect that the estimate to be exactly correct. But how much do samples results vary? Your teacher was, see, why he is giving us inference sampling? Because we are going to learn inferential statistics in the next topic, by the way. So that he is making our mind used to it that if we select different sample from a population, it may affect our output. Output means our prediction, our estimation, what we are doing estimation about our population. What do we do generally? We don't do calculation on the population. We generally do calculations on the sample that we have selected from the population. So in inferential statistics also, he will give us samples from the population, and what we generally have to do, we have to apply some inferential statistics on that sample and get some estimation that the population, if we launch a specific product, the average sale of the product will be this. In the next sample it may come this 76, in the next it may come 74, in the next it may come 55, in the next it may come 90, the sales, okay, of the product. So why this is varying? It is due to the sample changes, in the sample results changes in the estimation. So we shouldn't expect the estimate. So I'm reading this question again. When making an inference about a population from a random sample, we shouldn't expect the estimate to be exactly correct. But how much do sample results vary? Your teacher has prepared a large population of beads where 30% have a certain color, example red, so you can explore this question. In a moment, you will select a random sample of 20 beads. Do you expect that your sample will contain exactly 30% red beads? Explain your reasoning. That's a very good question. So, see, for example, I have three beads, okay? Red, blue, and this is white. So the thing that I have shown you, the probability of selecting red, how much it is? 1 by 3, correct? 0.33. Means 33%. 33%. Yes, yes or no? So he's telling that there are, for example, there are 33% is of red. So in a population, this is a population, for example, 30% have a certain color. Okay, 30%, 30% are colored. Okay, so what I have done from this population, I have selected a sample of 20 beads. 20 beads. Okay, now what you can say that these 20 beads, in these 20 beads, there are 30% red, na? He's telling, yeah, 30% red beads. How much is the possibility? So what you will say that there are 30% color beads in this population and other are 70% are white, correct? So from that
Yeah.
color, all that we are selecting should be red. Exactly 30%. So the chances of coming all 30% red means all the color beads red means 30% of 20 is 30 into 30 divided by 100. 0 0 means
60%.
six beads come red. Six red beads should be there. Six red beads. So what is the
Yeah.
probability? It in different samples, it may be there that the sample contains 30%. But in some, it may happen that there are 30% color beads in there will be 30% colored beads. 30% colored beads. Colored beads. As there are 30% colored beads in the population. So near about plus minus, but there will be a figure near to 30% in the sample also. But it will not be the case that 30% will be red. It may happen that there is a mixture of 30% colored beads. It can be 30% blue beads, it can be 30% yellow beads, depending upon the sampling,
Yeah.
it may happen. So that's the reason. So mix the beads thoroughly. Select a random sample of 20 beads of a population. Calculate the percent of red beads in the sample and replace the beads in the population. So you have to do it. What you'll say live at your home, you can perform it. After all students have selected a sample, make a class dot plot showing each student estimate for the percent of red beads. Where is the graph centered? How much does the percent of red beads vary? So you have to just see the variation in the red beads of the different samples, by the way. So imagine that you repeat steps 2 and 3 with random sample of size 100. So what we have done, increase the size of the sample. So how do you expect the dot plots would compare? If there is time,
Yeah.
select.
Give me 1 minute. I just need.
Yeah,
Can you give me 1 minute real quick?
yeah.
Huh? Yeah.
Yeah, you can take it. Yeah, take your time.
Okay, I'm back.
Okay. Okay. So now you can hear when this is stores class of 40 students with the red bead activity, they produce the dot plot shown at the left top for sample of size 20. The dot plot is centered around 30%. The true percent of red bead. This shouldn't be surprising because random sampling helps avoid bias. Notice also that the estimation varied from 10% to 50%. At the end, only 11 of the 40 estimates were equal to 30%. So see, 11 of the 40, 11 of the 40. That's the very means 40 samples they had taken, na? 40.
Mm.
11
Yeah.
of 40 samples means in that 11 only there were 30%. 11 samples had 30% red beads, 30% red bead. So when you calculate 11 by 40, how much it comes? 0
11 by 40, that's so point 26.
2 not 2 then it will be at 30 and 0 for 7 27 0
Oh, close enough.
0.27, that's 27%. I've told you or not. See, here also it is coming 30%. Yes or no? Yeah, so there will be some variability in that. So that's the thing. So sampling variability and sample size. Larger random samples tend to produce estimates that are closer to the population. Means if the sample size, if the sample size is larger,
Mm-hmm.
then it tends to produce estimation that are very close, are very close that of the population. That of the population means what? For example, I am collecting a sample size of 40, and I am collecting a sample size of 100. So which will correct better estimation? So less accurate estimation. Why I'm telling this? Less accurate, and here will be high accuracy also here. Here it is less accuracy estimation. Why? Because comparing with this, here it will be less and here it will be greater. Why this is greater? Because its sample size is greater. Yes or no, Zaid?
Mm-hmm.
That's the thing. So is it clear? Come on.
Yeah.
Read this question and tell me the answer.
Mm-hmm. Because for number A, it's no, because we need a bigger sample size in order to find out if the actual
Right.
average weight is 244.
Correct. Which would be more likely to give an estimation close to the true average weight of all NPL players, a random sample of 50 players? Correct. Yes. Okay, very good. Different sample
There's
size
100 players.
produce different average weights. So it would be surprising if the estimation is equal to the true average weight of all the NFL players. So it is exact when you are giving exact what you will say. I'll we'll see any asking questions about any exact point. Asking probability of any exact point is 0 means what will be the average weight of the NFL players, football players. So he is giving the 244.4. This is an exact value. So its probability is near to be 0 to be likely to be this average. It is 0. Why? Because you cannot rely on one point. It can vary. We have seen. And a random space of 100 players because estimated tend to be closer. So 100 sample size, it will be better than 51. Is it clear? That's the thing. So estimates from random sample often come with a margin of error. See, the thing that I was telling. So giving an exact range, it gives the probability 0. But when you are giving a range, means this is upper limit, this is lower limit, and this is upper limit. The average weight can come between these limits. So for example, I am giving 230, he is subtracting plus minus 14. So, and it is 258. That the average weight of the NFL player will come between this range. So its probability tends to 1. Here probability tends to 0 when there is a single value. And when there is a range of values, so its probabilities tends to be 1. That's the thing. Did you got that, Zaid? So when you are
Mm-hmm.
generally speaking, in our general reasoning also and conclusion, you should give a range that the average sale of a specific product will be between $2,000 to $2,500, by the way. So that's the thing.
Yeah.
So now we have seen inference of sampling means what is the inference of sampling. Now there's inference of for experiments. Next topic.
Yeah.
So what's in inference for experiment? Well-designed experiments allow for inferences about cause and effect. But we should only conclude that changes in the exploratory variable cause changes in the response variable. If the results of an experiment are statistically significant, significant is the word which is very oftenly used, or you can say very much used 90% in the inferential statistics. You will see every statement of the inferential statistic which start or with will have the word significant, significance. There are too much words in inferential statistics that you will see. So what is statistically significant? So when observed results of a study are too unusual to be explained by chance alone, are unusual to be studied by chance alone, the results are called he has given this definition in 2C, inference for experiment, and in that the statistical significance. Statistical significance means the results are not based on chances. The result, I write both the one in both the definitions in this here. The result does not depend on chances means does not depend on chances means what? Does not depend on probability, does not depend on
Probability.
chances, but changes in changes in explanatory variable cause effect on response variable, then it is known as statistically significant results. Means that the experiment that we have done is statistically significant. If it is happening based on the chances, then what experiment you have concluded, what observations you have made, that's the reason. Is it clear? So Mr.
Mm-hmm.
Wilcox and his students decided to perform the caffeine experiment from the preceding section. In their experiment, 10 student volunteers were randomly assigned to drink cola with caffeine, and the remaining 10 students were assigned to drink caffeine-free cola. The table and graph show the change in the pulse rate for each student, final pulse rate, initial pulse rate, along with the mean change for each group. So here that this is the case generally. Okay. The dot plots provide some evidence that caffeine has an effect on pulse rate. The mean change for 10 students who drank cola with caffeine was 3.2, which is 1.2 greater than for the group who drank caffeine-free cola. But are the results statistically significant? Recall that the purpose of random assignment in this experiment was to create two groups that were roughly equivalent at the beginning of the experiment. Subjects with the high caffeine tolerance should be split up into about equal numbers. Subjects with high metabolism should be split up in about equal numbers. So depending upon what you'll say, the differences and the what you'll say similarities, we have learned randomized block design where we used to make two blocks depending on the similarities. We have seen all these data in the these what you'll say experimental designs in the previous lectures. Yes, Anusai, what he is telling.
Yeah.
So of course, the random assignment is unlikely to produce groups that are exactly equivalent. So random sample is not good. Randomized block sample or match pair design we have to use. One group might get more favorable chances. Okay, so there are two ways to explain why the mean change in the pulse rate. Rid of caffeine group. Okay, that's he's explaining. Okay, we'll read it. It's important. So caffeine does not have an effect on pulse rate, and the difference of 1.2 happened because of chance of variation in the random assignment. So these all things we have studied. That, for example, if there are 10 students that we are what you will say experimenting on, these are the subjects, our subjects, and 4 are caffeine addicted. Caffeine addicted now that they are drinking caffeinated cola from years, and they are non-caffeine addicted. They are not addicted to caffeine, and they are not drinking caffeinated cola or caffeinated things on a regular basis. And here they are drinking on a regular basis caffeinated products. So now what will happen when we are doing random assignment directly from here? So it may happen that we have taken 5 and we have taken here 5. So in this 5, 4 are caffeinated addicted, and here all 5 are non-caffeinated addicted, and one is only non-caffeinated addicted. So what will happen? This result will show a high variation. Yes or no? These things I have discussed in the previous class. I'm just repeating it for revision. There will be a great variation. Great. So directly randomized sample does not help to get good results. But when we'll do random sample from here, means we'll make a group of 2 year. Okay, this is block that we are made. So we have made for year 3 and 3, and now we'll give caffeinated cola, non-caffeinated cola, caffeinated cola, non-caffeinated cola, and now then we'll measure the output. So now this compare, and now then we'll compare. So this will not show any variation, greater variation in our results. What is the true case? It will show that way. Is it clear?
Mm-hmm.
Yes or no?
Yeah.
Yeah, so that is a activity based on the what you'll say offline activity that you can generally do and see the variations in the things. So gather 20 index cards to represent the 20 students in the experiment. On each card, write one of the 20 outcome listed in the table. For example, write 8 on the first card, 3 on the second card, and so on. Shuffle the cards and delay 2 pipes of 10 cards each. This represents randomly assigning the 20 students the 2 treatments. Assuming that the treatment received does not affect the change in the pulse rate, the first pile of 10 cards represent the caffeine group and the second pile. Oh, fine. Find a mean change for each group and subtract the means. Note, it is possible to get a negative difference also. Your teacher will draw a label and access for a class dot will plot the differences you got in the step 3 on the graph. So you can do this. So you will understand that in Mr. Wilcox class, the observed difference in mean was 1.2. Is difference of 1.2 statistically significant? Discuss with your classmate. So it was not, I think, so statistically significant because the things was the sample space was very small. The first thing, we have to increase the sample space. Second thing, we have to get a randomized block design. The randomized block design means based on their characteristics, similar characteristics, we have to make the blocks, and on that blocks we have to perform matched pair design. So the matched pair design that we have learned in the last matched pair design. What we used to do, block of 2 you have to make on the similar and give. I'm repeating this because one. Okay, first day First day, for example, caffeinated cola, non-caffeinated cola. Okay, in the second day, he'll refuse a non-caffeinated cola, and then we'll compare. This comparing is the best, which matched pair design. So matched pair design when we will use on these experiments, so then only our values will be statistically significant, by the way, by taking a large sample. Is it clear, Zaid?
Yeah.
Yeah, so see, that is 19 times the difference was 1.2 on the greater. Yes. So dot plot showing that so because of difference of 1.2 or greater and somewhat likely to occur by chance alone, the result Mr. Wilcox class experiment aren't statistically significant. Based on this experiment, there isn't convincing evidence that caffeine increases pulse rate. So distracted by oh, now read this question. Come on, just give me a minute. You
Yeah.
read it. Okay, I'm not great. Don't give me the answer.
Mm-hmm.
So what's the case? So calculate the difference passenger cell phone in the what he's trying to measure the difference is that while talking on a cell phone while driving a car or while talking to passengers that are sitting behind while driving car, which distracts the driver the most. So
Yeah.
while
Okay.
talking on a cell phone and the other have to drive in the simulator, one response variable was whether or not the driver stopped at a rest area that was specified by the researchers before the simulation starts. So what's the case? For example, this is a driveway. Okay. For example, the researchers has given the stop area here and here as the stop area. For example, two, we do cannot draw a long road. So the driver starts, driver one and the driver two. So he's talking to a passenger, and talking on cell phone. So what we'll do, we'll start the drive. So we'll see whether driver one stops on the both the what you will say resting area, or driver one stops on both the resting area, or driver two who stops the most on the stopping areas or the resting areas. By the way, so calculate the differences in the proportion of students who stopped at the rest area in the two groups. 100 trials of a simulation were performed. 100 trials. 100 trials means 100 times he has experimented this simulation. Were performed to see what differences in proportion would occur due only to chance variation in the randomly assignment, assuming that the type of distraction will not affect whether a subject stopped at the rest area. That as 33 stoppers and 50 non-stoppers were randomly assigned of two groups of 24. There are three
Mm-hmm.
dots at 0.29. Explain what these dots mean in this context. Use the results of the simulation to determine if the difference in the proportion from part A is statistically significant. Explain your reasoning. So this is the thing. See, stopped at the rest
Mm-hmm.
area, didn't stop. So cell phone users, the driver who were talking to a cell phone and on a passenger. So this is the data and this is a dot plot. So what you have to explain in the first question. So there's difference in the proportion. So what's the proportional difference? That while the passengers stopped at the rest area and while he was talking to a passenger, so what's the proportion? It is 21 upon 24 minus 12 upon 24. So it is round about the variation is here it is 12 na? In this
Mm-hmm.
12 upon 24 yes na? Yeah, 21 upon yes 21 upon 24 and this 12 upon 24. So what was the variability in both of them? So that's the thing. This is the difference in the proportion of both the cases where stopped at rest area while the driver was talking to the both. Okay, when we assume that the type of distraction doesn't matter, there were three stimulated random assignments that were different in the proportion of the student who stepped at the rest area was 0.29. 0.29. So because the difference of 0.375 or greater never occurred in the simulation, the difference is statistically significant. So seeing this dot plot, you can see that it is normally distributed dot plot. Okay, and there is no much variance in it. So therefore, it is statistically significant. Is this clear?
Mm-hmm.
So the scope of inference. So what is the scope of inference? It is based on the differences in the output that we are getting. So we will use this. So the scope of inference. So randomly selection of the individual allow inference about the population from which the individual was chosen. So it is very true that random selection of individuals, when we do random selection of the individuals, it allows that our conclusion about the population from which the individual was chosen will be correct. And random assignment of the individual to two groups allow the inference about cause and effect. So when we do random assignment to the treatment, random assignment is done to the student based on the groups. So it generally gives us better in things upon cause and effect. What are the cause and effects on it? Is it clear?
Mm-hmm.
So that is the thing. There is one more activity that you can read it by through. You have more 5 minutes. We'll complete this.
Huh?
You have more 5 minutes. We'll complete
Yeah.
this.
Okay.
Yeah,
Mm-hmm.
just 5 minutes. We'll complete this topic. Okay, so Come on, read this. So researchers at the University of North Carolina were concerned about the increasing the dropout rate in the state high school, especially for low-income students. Surveys of a recent dropouts revealed that many of the students have started to lose interest during the middle school. They said they saw little connection between what they were studying in the school and their future plans. To change this perception, researchers developed a program called Career Start. The central idea of the program is that teachers show students how the topics they are learning about can be applied to specific careers. To test the effectiveness of Career Start, the researchers recruited 14 middle schools in Forest County to participate in an experiment. Seven of the schools determined at random used Career Start along with the district standard curriculum. The other seven schools just followed the standard curriculum. Researchers followed both groups of students for several years, collecting data on students' attendance behavior, standardized test score, level of engagement in the school, and whether or not the student graduated from high school. So, result students at the school that used Career Start generally had significantly better attendance and fewer discipline problems earned higher test scores, reported greater engagement in the class, and were more likely to graduate. What conclusions can we draw from the study? Explain your reasoning. So, generally, not reading the answer that's given in the text, but what is the thing that career start affects the personality of a student, whether personality and academic performance of a student. So, career start is good. It should be started in all the schools. That can be conclusion because treatments were randomly assigned and the results were significant. As it is random assigned treatment, and we have learned here in this scope of inference. When is the best scope of inference? When random assignment and random experiment is done. So we can conclude that using the career start curriculum caused better attendance, fewer discipline problems. Where there were many discipline problems, it reduced to fewer. Higher test score, greater engagement, and increased graduation rates. However, these results only apply to schools like those in the study because the schools were not randomly selected from any population. So these were the things that we have chosen for that specific school that we have chosen because school was not chosen on a randomly basis. It was selected schools. Therefore, based on all the schools, it is not statistically significant. But for a specific school, it is statistically significant. Means for there is school A, okay, and school A, and it come to be statistically significant that career start career start affects results. For example, I cannot conclude for school B. Cannot be concluded. Cannot be concluded. Why? The same result? Because school was not randomly chosen. School was not randomly chosen. That's the thing.
Frozen?
Is it?
Yeah.
Yeah, that's the
Mm-hmm.
thing. Okay. So the changes of establishing causation and this all, I think we have done this. Yeah, done this chapter almost. Okay, we'll look into it and we'll stop. Okay. The changes of establishing caution. A well-designed experiment can tell us that changes in the exploratory variable cause changes in the response variable. So means well-designed experiment has a good rate of changes when we are changing the exploratory variable. More precisely, it tells us that this happens for specific individuals, specific environment of the specific experiment. In some cases, it isn't practical or even ethical to do an experiment. Consider these important questions. Does going to church regularly help people live longer? Does smoking cause lung cancer? To answer these cause and effect questions, we just need to perform a randomized comparative experiment. Unfortunately, we cannot randomly assign people to attend church or to smoke cigarettes. Yes, that's the thing. So some experiments are not what you'll say good to carry out by the way, and we cannot measure the devotion of a what you will say a person towards God by just randomly assigning the things by the way. Okay, that's the thing. Okay, so these are several criteria for caution when we can't do experiments. So these caution means what things we can do when we are not in the what you will say environment of performing an experiment. So doctors have long observed that most lung cancer patients were smokers. Comparison of smokers and similar non-smokers showed a very strong association between smoking and death from lung cancer. Could the association be due to some other variable? Is there some genetic factor that makes people more likely to become addicted to nicotine and to develop lung cancer? that sees the study. Based on the study, we can do it. So there are several criteria for establishing caution when we can't do an experiment. The association is strong. The association between the smoking and lung cancer is very strong. The association is consistent. Means consistent means it doesn't show very much variation in the things. Larger values of exploratory variable associated with stronger response. Then these are the establishing caution. Means what caution we can take. What we cannot generally perform the experiment, so we will rely on our observational studies that we are making. Is it clear, Zaid?
Mm-hmm. Yeah.
Data ethics, inshallah, we'll do it tomorrow and finish off this chapter and see some of the sums and then move on to the next chapter. Is it clear? Okay?
Yeah.
Okay. Thank you very much. You can leave, Zaid. Assalamu
Okay.
alaikum.
Assalamu alaikum.
Islam.